Work, energy, and power. This is a long video, but that's because it's very comprehensive. So there are some things you should know by now, such as the work in physics means a product of force and some kind of distance, which I'll clarify in a bit, so don't worry. Also, you should know that energy is related to work in that we define energy as the capacity to do work. And finally, power is the rate at which work is performed or energy is consumed. The SI unit for power is the watt, which is 1 joule per second. So here are the table of contents for what we're going to be covering in this video. So we should start with mechanical energy. And generally speaking, mechanical energy can be thought of as the sum of both the potential and the kinetic energy of an object at a specific moment in time. Now, kinetic energy we talked about already, and kinetic energy is the energy that an object which mass has, which is due to its velocity and has the equation K for kinetic energy equals 1/2 mv squared, where m is mass and v is velocity. You should also note that the other equation we looked at before, which also had mass and velocity in it, was momentum. Momentum is equal to mass times velocity. We called it inertia with motion, so that was mass times velocity. This time, kinetic energy is similar, but the equation for kinetic energy is 1/2 mv squared. So if it's moving, it has kinetic energy. Potential energy. So there are a few different types of potential energy because just as it sounds, potential kind of means possible or future energy. Chemical or electrical potential energies are two types of important potential energies but are outside of the scope of this course. In this course, we will be concerned with two particular types of mechanical and potential energy, which is gravitational potential energy and elastic potential energy. So we'll first talk about gravitational potential energy, and if you hear a lot of noise in the background, it's my water heater, I apologize. Anyway, for this course, gravitational potential energy is specific to the inertial frame of reference of being on Earth. What that means is these problems imply that we are on Earth, and therefore little g, which equals 9.8 meters per second squared, or negative 9.8 meters per second squared, applies. So we could simplify our equation to say U equals mgh, where U is potential energy, and the SI unit for potential energy is joules. M is mass, the SI unit is kilograms. G is the gravitational acceleration constant on Earth, that's little g, and that is meters per second squared, or meters per second per second. And h is height, which is a displacement, and therefore it is in meters. Elastic potential energy. Well, to think of elastic potential energy, think of stretching or compressing a spring or a rubber band. When you let it go, it springs back in the opposite direction. And the elastic potential energy equation is given as U equals 1/2 kx squared. Looks a little bit like the kinetic energy equation, but it's not. It's potential energy it's elastic potential energy. So U, again, is our potential energy variable, again measured in joules. K this time is something called the spring constant, and please note that that is little k or lowercase k, not capital K, which is what we were using for kinetic energy. So lowercase k is the spring constant, and then x is our displacement, so x squared would be the square of displacement. Since the SI unit of displacement or length is the meter, x squared must therefore be meters squared. It follows then that the unit for spring constant, in this case, should be the joule per square meter, simply because we could solve the equation for K, saying if we divide both sides by 1/2 x squared, we will get 2u over x squared equals K, and since 2 is a constant, we can get rid of that, and u is joules, x squared is meters squared, so we would end up with the spring constant unit of joules per square meter. If you didn't follow what I just said, rewind it and re-listen to it. So now we should talk about Hooke's law, and we talked a little bit about Robert Hooke in class, so I'm not going to go down that tangent right now. But Hooke's law is basically stated F equals kx. The force used to distress a spring by a certain distance x requires a particular spring constant K. So in other words, if I have a large spring constant, that means it's really hard to stretch or compress the spring a certain distance. So therefore, as the spring constant goes up, the force must necessarily go up to stretch it that distance. And that's all Hooke's law is. For a Hookean spring, that follows true. F equals kx, sometimes you'll see it as F equals negative kx, and this is all in how you define the problem as to whether or not you're talking about the force to stretch the spring or the force to compress the spring or the compressive force. Continuing on with Hooke's law, so again we said F equals kx. If we were to solve for k, we would get k equals F over x, which therefore means the spring constant must have the units of newtons per meter. But just a couple moments ago, we said the units of the spring constant was the joule per square meter. So now we should talk about the joule, and this is James Prescott Joule, and the joule is the SI unit of both work and energy. Some of the equations we've covered so far is the gravitational potential equation, energy equation, which is U equals mgh, the generic work equation, work equals force times distance of some kind, and K, kinetic energy, equals 1/2 mv squared. Again, I will clarify that work one. I'm leaving it vague on purpose for now. So here, all I did was I expanded each of those equations by substituting in the units. So in the first one, U equals mgh, well, the SI unit for mass is the kilogram. The SI unit for the gravitational constant is meters per second squared, and the SI unit for height is the meter. So you end up getting the kilogram meter squared per second squared. Then let's look at the second equation. W equals force times distance. Well, that equals newtons times meters. So newtons times meters, if we then recognize that F equals ma from Newton's second law, 1 newton must therefore equal m, which is kilograms, times a, which is meters per second squared. And then when we substitute back into the n times m equation, we get the kilogram meter time meter per second squared, which is the same thing as the kilogram meter squared per second squared, just like the one above it. Lastly, if we look at the third equation of kinetic energy, we get 1/2 mv squared, where again, m is mass, kilograms, v is meters per second, and you square it, so you get the kilogram meter squared per second squared. All three of these have exactly the same units, and each of those is equal to the joule. So back to the spring constant units. The two that I looked at before when we looked at the potential energy, the elastic potential energy equation, it was U equals 1/2 kx squared, and we got the unit for K is the joule per square meter. And then when we looked at Hooke's law of F equals kx, we got K equals newtons over meters. And now we're going to see how they are exactly equal to each other. They are the same thing. So the joule, like we said in the previous slide, is really the kilogram meter squared per second squared. We can substitute that in for the J and the joules per meter squared, and you will end up with the equation at the bottom of this slide here. You'll get the kilogram meters times meter over second squared, all of that over meters squared, and you can cancel out those square meters, and you end up with kilograms over second squared. And then, if we do the other side, we know that the newton is the kilogram meter per second squared from F equals ma, so we substitute that in for the n in the n over m, and you get kilogram meters per second squared over meters, and you get the kilogram over second squared. So in both of those, the joule per meter squared and the newton per meter, they both reduce down to the kilogram per second squared. Now wait, what in the world is the kilogram per second squared? Well, the kilogram per second squared is mathematically the exact same thing as the joule per meter squared and the newton per meter. And I'm not really sure, but I think the newton per meter is used because of the three, that's the one that's most easy to visualize. If you think about it, newtons per meter is something you can envision because newtons is a measurement of force and meters is a distance. So if you're thinking, okay, there's 50 newtons per meter, is at least a value that you can kind of visualize. Joules per square meter, That's a little bit harder to visualize, but again, that's not too bad. It's kind of like energy pressure. If you think of pressure as force divided by area, well, now we're thinking energy per unit area. Okay, it's a little bit harder to visualize, but you could maybe have an abstract idea of it. But what in the world is the kilogram per second squared? That is mass over square seconds. What does square seconds even mean? And because of that, no one uses the kilogram per square second. And most of the time when you see spring constants, it's going to be something with force over distance, like Newton over meter. So now we get to the work-energy theorem, which is one of the more important theorems that we're going to come across in this course. And the work-energy theorem says that the net work done on an object will change that object's kinetic energy. Specifically, W net equals delta K, where W net is the net work done by a net force along a displacement. And delta K is the change in kinetic energy, also equal to 1/2 mv final squared minus 1/2 mv initial squared. So the work energy theorem, let's think of an example. Imagine you are in a supermarket with a shopping cart. It's loaded down and you see an open checkout lane, so you aim your cart and you push harder. You are doing work on the cart. Due to the work energy theorem, you must therefore increase the kinetic energy of the cart. Since you aren't adding or removing mass from the cart, the only other variable that could change is the velocity, which goes up as a result of you pushing it. And again, this makes sense from Newton's second law. When you provide a force, a net force that you provide onto the cart, you are going to accelerate the cart because F equals ma. And when you change the kinetic energy, you are changing the velocity component there. So 1/2 mv squared becomes 1/2 mv final squared. So in the green section here, you are speeding up, which means you are supplying a force over a certain distance and therefore doing work to the shopping cart. In the blue section now, you've hit top speed and you just continue moving at constant velocity, which means there's no net force and therefore no work is done on the cart during that portion of the trip. So really, only the green section, that distance, experiences the work. Now, the work energy theorem also works in reverse. Imagine now you are headed straight for the checkout line when now someone else veers in front of you, stealing your place. So now you throw your hands up in frustration, and due to Newton's first law of inertia, your cart crashes right into the other customer and comes to a painful stop. Since it started with a velocity and it ended stopped, in other words, velocity was 0, and it didn't lose any mass, there was a resulting change in kinetic energy. And from the work energy theorem, work must have been done on the cart to bring it to a stop, thanks to the unsuspecting customer you crashed into. That distance that it traveled was maybe as the cart impacted the person and caused their knee to buckle or something, and it came to a stop. So that distance multiplied by the force of the impact was equal to the work done onto the cart, which caused it to lose the kinetic energy. This is very similar to the impulse momentum theorem. The impulse momentum theorem says that force multiplied by a time interval, in this case the force of impact multiplied by how long that impact occurred, is equal to the change in momentum of the cart. The cart was moving, the mass stayed constant, and now it's stopped. So these two are very closely related. Now we need to talk about conservative and non-conservative forces. A conservative force is a force in which work done by or against it depends only on the starting and ending points of a motion and not on the path taken. Gravitational force, or weight, and spring, or elastic, force for Hookean springs are common conservative forces. Now, because the force is path independent for a conservative force, we can define a potential energy by any conservative force as a result of the difference between its final configuration and its initial configuration. So maybe that last explanation was a little bit tricky. This is the Wikipedia entry, which I also like, and I'm going to read the part in the red box which says, A conservative force is dependent only on the position of the object. If a force is conservative, it is possible to assign a numerical value for the potential at any point. When an object moves from one location to another, the force changes the potential energy of the object by an amount that does not depend on the path taken. So imagine then that there's a ball. It is sitting on the ground. The potential energy is 0 because it's not going to, if it falls, where's it going to fall? It's not going to fall anywhere, so it's at 0. But now you pick up the ball and you raise it 3 feet off the ground. All you did was you changed its configuration. It is now 3 feet above the ground, so now it has a potential that is 3 feet off the ground. Because you lifted it 3 feet off the ground, it has a potential to fall all the way back down to 0. So that's kind of what this means by assigning a numerical value. You can set a relative 0 value, and then however far away from that 0 you get is your potential, as long as you're in the same direction as the force, the conservative force. Like if you move the ball sideways, it doesn't change the potential energy. It only makes a difference if you lift it up or down. So what about non-conservative forces? So a non-conservative force is a force for which the path actually matters. And friction is the classic non-conservative force, and there's a pretty good picture in the book, which is figure 7.14, and it shows an eraser going from point A to point B in figure A, and then again from point A to point B in figure B, but it takes a different path. But it does more work because it is erasing more, right? The eraser, as it covers more ground, generates more friction on the paper and does more erasing work, right? So friction is a non-conservative force. It definitely matters what direction you go with this, or the pathway for the force being applied, and it must be calculated as such. So now, when we revisit the work-energy theorem, remember I said W net, the net work. Well, it must be noted then that net work has to include both the work done by conservative forces and the work done by non-conservative forces. So ultimately we end up with the equation at the bottom, which says W conservative plus W non-conservative equals W net, which equals delta K. And that is truly the work-energy theorem. So what is work anyway? Up to this point, I mean, I've been pretty vague on work, and this was intentional because there isn't a great way to explain it without having to re-explain it, so I gave it to you in a very bare-bones method. I said that work was equal to the product of force and distance of some kind. Some of you even asked, did I mean displacement instead of distance? And hopefully the last section about conservative and non-conservative forces might begin to shed some light on the actual answer to that question. So this is work in its purest form, and there is some calculus here, and many of you, most of you maybe, are taking calculus, or you have already taken calculus, and if not, don't worry about it, because I'm only showing you this part for the explanation of what work really is. And work really is the area under the curve of the force times distance equation. So if you think of it like that, C is the pathway, and we're looking at the integral of f ds, where f is a conservative force and ds is an infinitesimal displacement. And as it expands out, again, Wikipedia does a good job here, so I just cut and pasted from there. But what you can see is work must therefore then equal the potential energy, or the change in potential energy, the change in potential energy, and that's why U of x is the potential energy equation here. So now let's examine gravitational potential energy through a slightly thicker lens. And what we find is that integrating the conservative gravitational force, which is weight, which equals mass times gravitational constant, with respect to vertical distance, delta H, results in a gravitational potential energy, just like we said before. And here we say U gravitational equals mg times delta H. In other words, what we think of as gravitational potential energy is really just a result of the work done on an object due to a change in its vertical position in line with a conservative force known as weight. Therefore, the higher you lift an object, the more vertical or the more gravitational potential energy it had than when you started. Non-conservative forces also do work. So we know that conservative forces that do work on an object will raise the object's potential energy. It transfers energy by doing work. We also know that net work is the sum of the work done by conservative and non-conservative forces, and it will result in a change in kinetic energy. But how do we determine work done by non-conservative forces? So here we have another work equation, and if you read the book, you probably came across the following equation: W equals FD cosine theta. In fact, that's equation 7-2 from the book. Specifically, the book says, formally, the work done on a system by a constant force is defined to be the product of the component of the force in the direction of motion and the distance through which the force acts. But why cosine? So imagine then you have this black box, it's like a hockey puck, sitting on a frictionless surface. If you apply that diagonal green force, it will end up moving along that surface to the right, right? I mean, correct? So therefore, the component of the force which is in the same direction as the motion is the force that actually provides the motion, and therefore the component equals force times cosine of theta because that is the adjacent component. So really the equation should read W equals F cosine theta times D. However, you often see it as FD cosine theta, but really what it means is F cosine theta, that's the component that's in line with the direction, multiplied by the distance. So here's another mathematical thing. I talk about this in the Physics C course, but it's worth mentioning here. And this is the scalar product, also known as the dot product. A vector magnitude alone, as in it still has units but without direction, is a scalar. And in a physical sense, it means something despite its lack of direction. So for example, 65 miles per hour definitely means something, and that something is a speed, regardless of what direction you're headed, which ultimately would make it velocity. Speed is still a magnitude, which is a number multiplied by a unit, so 65 miles per hour. In a similar sense, mechanical work is a scalar product of force and displacement. The mathematical operation, which is called the scalar product or the dot product, is the product of the magnitudes of each vector and the cosine of the angle between them. So A dot B really means AB cosine theta. So you should really see that work is truly W equals F dot D. In other words, work is the dot product of force and displacement. Ramifications of the dot product. The dot product, again, it's called the scalar product, and this is because it yields a scalar for an answer. This is why work and energy are scalars and they are not vectors. There is no direction on work or energy. In fact, that's often a question that pops up on standardized tests. So you should know right now, work and energy are scalars, they are not vectors. If angle theta between the two vectors is 0, that means the two are in line with each other and the work is maximized, meaning work is simply force times distance. On the other hand, if the angle theta between the two vectors is 90, then work is minimized and work is 0, which makes sense because how could you push a box horizontally and have it go up in the air, right? I mean, if you are pushing in a direction opposite to the direction of motion, I mean not opposite, perpendicular, it's not going to change anything. So a summary about work. It should be a little clearer now why I was so vague on the definition of work. It's a complex beast if you think about it. It's the product of two vector quantities, but it's not a vector. And sometimes the path matters, a non-conservative force such as friction. Other times it doesn't, conservative forces such as gravity. And thus, a blanket statement like work equals force times displacement or work equals force times distance are misleading without additional qualification, and that's why I didn't want to say either one of those when we were first talking about work. So now we get to pretty much the most important big idea in maybe all of the science classes, the conservation of energy. The total energy in any process remains constant. It may change in form or be transferred from one system to another, but the total must remain the same. And until you take all the other science courses, you won't truly come to an appreciation of how wide, how broad-reaching this statement truly is. But because physics is the most fundamental of all of the sciences, from which then chemistry branches out, and then from chemistry you can spawn biology and so forth, I mean, this is really fundamental to all of the sciences. So it's kind of like, of all the big ideas, this is probably number one. So the conservation of energy. The work done by conservative forces result in potential energy. We said that earlier. Work done by both conservative and non-conservative forces result in a network which changes the kinetic energy. That's the work energy theorem. And so, U naught plus K naught plus WNC plus OE naught equals U plus K plus OE, where the naught subscript indicates an initial state. So U naught is initial potential energy, and K naught is initial kinetic energy, and OE simply means other energy, which we must account for, but right now we're just going to assume that it remains constant throughout. So the conservation of energy equation is kind of comprehensive. It says all of the potential energy and all of the kinetic energy that we start with, plus all of the work done by the non-conservative forces, plus all of the other energy that we start with, must equal all of the potential energy plus all of the kinetic energy plus all of the other energy that we end with. The conservation of energy is so fundamental. In other words, what goes in is what comes out with respect to energy, just like the conservation of mass used in chemistry, and it is so powerful. Assuming no friction, a non-conservative force, I can predict the velocity of the ball at any point on this curve, provided I know the difference in the height, which is a delta y. I'm going back to delta y instead of delta h now, because we use delta y in the kinematics, and h we use for height, delta y is for vertical displacement, or vertical change in position, which results in a displacement. So let's look at this problem. Let's simplify the problem to say that only conservative forces are in play. In other words, there's no friction. We could say that the ball starts with 0 meters per second velocity, and it starts at a point 3 meters above the ground. When it gets to a point at the end, which is 1.2 meters above the ground, how fast is it going to be going? We can solve this using the conservation of energy. The conservation of energy states that the total mechanical energy must remain constant, or in other words, U naught plus K naught equals U1 plus K1 equals U2 plus K2 equals ... U plus K, or U final plus K final. So what we're looking at is we're starting here where initial velocity is 0, and we're starting at a height of 3 meters. And we're finishing at a point where we don't know the velocity, but that's what we want to know, and it's at a height of 1.2 meters above the ground. Our initial kinetic energy is the kinetic energy equation with initial velocity, so that's 1/2 mv naught squared. Our initial potential energy is mg h naught, so we just changed the h to a y, so mg y naught. Our final kinetic energy is 1/2 mv squared, v being the final velocity, and our final potential energy is U equals mgh, which, again, we're changing the h to a y. U equals mgy. And the conservation of energy states that the energy at the start must equal the energy at the finish. So U naught plus K naught equals u plus k. So let's look at the solution here to this problem. From the conservation of energy, we say that u naught plus k naught equals u plus k. Expanding that, we get mg y naught plus 1/2 mv naught squared equals mgy plus 1/2 mv squared. Again, all of the starting values I'm going to keep in yellow, all of the finishing values I'm going to keep in blue. So factoring out the m's, because you can factor out mass on both sides, which turns out to be a very powerful operation here and has other ramifications that we'll talk about later, but you'll get gy naught plus 1/2 v naught squared equals gy plus 1/2 v squared. Simplifying that, you will get gy naught equals gy plus 1/2 v squared. And I say simplifying that because v naught is 0, and therefore we can cross that out. So now we get gy naught minus gy equals 1/2 v squared. All I did was I brought the gy over to the other side. And now I divided both sides by 1/2, which is the same thing as multiplying it by 2. And so you end up getting 2 times the quantity of gy naught minus gy equals v squared. Expanding that out then to solve for v, we get v is equal to plus or minus the square root of 2 times the quantity of gy naught minus gy. Factoring out the g, we will get that, and then you substitute the numbers in, and ultimately you should arrive at the answer of v equals 5.94 meters per second. So you start off at 3 meters above the ground with 0 velocity. If you are frictionless, by the time you get to a height of 1.2 meters, no matter how you get there, you will be going 5.94 meters per second thanks to the conservation of energy. Let's look at another problem. Here's a slider. It has a mass of 5.90231243256777 kilograms and is traveling at plus 3.92 meters per second. Assuming no friction, how high off the ground will the slider get on the ramp, which has an angle of 27.42635746868656 degrees when it comes to a brief stop before sliding back down? I want you to try to solve this. So you might be thinking, wow, that's a super significant mass and that's a super significant angle, but the fact of the matter is you don't need either one of them to solve the problem. In fact, due to the conservation of energy, all we need is initial potential energy and the initial kinetic energy, and that's going to equal the final potential energy plus the final kinetic energy. To start, let's call our initial height 0, and we can come up with our 4 energy equations here. We could say initial potential energy equals mg y naught, but that's going to equal 0 because we just said y naught is 0. We're calling the first height there 0. That's our reference point. That's our 0. Now our initial kinetic energy, the object is moving at 3.92 meters per second, so we will have a kinetic energy initial, and that is 1/2 mv naught squared. We know that it goes to a final height, so therefore there better be a final potential energy, and that will equal u equals mgy. However, the final kinetic energy is 0 because it briefly comes to a stop, and therefore the v is a 0, so the whole kinetic energy becomes a 0. So we could get rid of that. So ultimately, through this convenient equation, we are now reduced to saying initial kinetic energy equals final potential energy, and therefore 1/2 mv naught squared equals mgy. But we can further reduce this by factoring out the m's. And now we're given 1/2 v naught squared equals gy. And we could go on to solve this problem, and what you ultimately find is if you are traveling at 3.92 meters per second at a ground level of 0, and it's frictionless, you will ultimately get to a point of 0.786 meters above the ground, no matter what path you take, no matter how steep the angle, no matter whether you go up and down a couple times before you get there or not. Assuming no friction, you will end up at a maximum height of 0.786 meters above the ground. powerful stuff, this conservation of energy. And that, now I think you can take a deep breath because we are done for now. Thank you for watching.